everyone. Guys, thanks for being here today. This is a different one, but it's an interesting one because we're going to be doing some real end-to-end workflow with M-Star, less of this like theory and more of just how we build these models, how we run these models, how we interpret these models, and the best practices for all three of those stages in terms of building, setting up, interpreting, etc. So again, this is more of a hands-on tutorial, which will show you not just like about the science, but also implementation and workflow within the context of the code. So I'm excited to present this today. The agenda is pretty simple before I jump into the hands-on demos. First, I want to speak about the GPUs making this possible. And at some point, I'm going to sound like some NVIDIA salesman. I'm not an NVIDIA salesman, but gosh, these things have revolutionized the types of models we can develop. And I've got to emphasize the difference these guys present and what they allow us to do. I'm going to talk briefly about the basic physics here. This is not one of my physics lectures. We've got a dozen of those on tape. This is much more implementation and using the code. So I'll go over this rather quickly. I'll talk about the data that we're referencing against, the measured data available in the literature that we're using to compare our model against and validate our model against. And then I'll go through this end-to-end example. And again, our picture here, our agenda here today is to do this holistic, three-dimensional, time-accurate simulation of, in this case, an XCR 2000, where we have gas flow bubbles. I don't know if you can see this here, informing the time evolution of the dissolved oxygen concentration. We have glucose being added to the system, viable cell density as well. We may not get all the way to these cellular mechanics today, but we'll definitely do the multi-phase flow, blending, oxygen transfer, KLA, oxygen dead zones, all of that multi-phase physics today, inclusive of metabolism to include O2 consumption and CO2 production, all within the context of the time-accurate three-dimensional flow simulations. So our goal today is bioreactors, our goal today is process simulation, our goal today is best practices within the context of these multi-phase simulations. Guys, I've used this slide multiple times because I want to hammer it. It's all about the GPUs. GPUs, just for those who may be a bit unaware, are not a new, but a quickly emerging and quickly, I'd say, popularizing computer architecture. They are incredibly compute dense. They can contain thousands of compute cores. They snap into a conventional desktop computer. They need a CPU to run them. You can look at my previous talks to learn more about this. But the key point is this, is they offer a tremendous compute density that allows us to run simulations orders of magnitude faster than what would typically be achieved on a CPU. Now, importantly, not all codes run on GPUs very well. And there was a paper that came out just last month that I wanted to speak to. That's probably it's called it up. That thought really hammered this point home. Just because that was diversion. This is in chemical engineering science, published again just a couple months ago by University of Manchester and Unilever. And they're like, let's just do some simulations. This was not bioreactors, but it's pretty close of miscible fluids. This could be like a glucose water type thing. But at the end of the day, the real point is this. They go through all this validation. They're using M-Star. They go through all this validation, and they make these kind of interesting comparisons down here, why the GPUs matter. And they're in this case, they're using M-Star, they're using a tool called Star CCM. And here's where they speak to it. Like the M-Star method, leveraging the parallel processing capacity of GPUs, a smaller time step required about 4 hours to complete the simulation. On the other hand, the Star CCM, 41 days. Like that's the difference, guys. This isn't when I'm talking about GPUs. This is why I get so emphatic and excited. This isn't like a Honda versus Toyota. Like this isn't like Nike versus ASICS. Like this is Delta Airlines versus a bicycle company in terms of the speed at which these things get done. You might say, oh yeah, well, they're both means of transportation. Yeah, like one changes how you live. Like, yeah, shoes and planes both get me across the country. But one is a lifetime event and one is this afternoon. There's a foundation that you got to understand like what this means in terms of how we simulate and how we change simulation. Like so many people are using simulation as kind of this big like production where it's like, oh, I'm going to, spend weeks getting ready for it. It's going to take months to run. Guys, when you can run these things in minutes and hours, as we'll do right now, it changes how you use these tools altogether and how you optimize them. So foundationally, again, it's astounding what these things can do when you have a code that exploits them to their full potential. And that's what we're talking about. When you what to months takes hours, that's a big change and why we got to keep our eye on them. Now, this speed doesn't just mean we run the same stuff faster. It means we can also interrogate physics at a more detailed level, okay? Like when we're doing multi-phase flows here, we're not doing some alphabet soup population mouse model. Never. We're doing explicit resolution of all the bubbles moving through the system, whether there be millions, tens of millions of them, as it were. We're looking at individual bubble breakup and coalescence events. We're doing LES simulation, watching the eddies discharge off the impeller and move throughout the system. So we're moving towards this continuum / transport carrier level description of matter. And what this allows us to do is develop more fundamental, more general, and less parameterized models. That is, when we're describing bubble breakup of coalescence at the level of bubbles interacting with an eddy and ripping apart to form two new bubbles explicitly, and resolving two bubbles coming together to bounce and or coalesce, the physics driving that, as it were, are much more universal than some overly parameterized 12 bin population model. Okay, so we always appeal to these more foundational approaches because we have the GPU horsepower that allows us to take our models down to that regime. Okay, so it's all LES, it's all DNS, it's all carrier level physics. Here are the kind of key equations we're solving today. I didn't show the Newton's second law for the particles, but that's easy to infer. We're going to be talking a lot about momentum transport as solved via the Navier-Stokes equation, represented by an LES model, okay, where I use the Smagorinsky model, Lillie-Smagorinsky model here, that informs the local viscosity of the Smagorinsky coefficient and the local shear rate. Species transport is modeled using a conventional conservation of species equation, inclusive of diffusive, convective, source, and reaction terms. We're going to be considering source terms, that is via bubble transport from each individual bubble to the surrounding fluid, as well as reaction terms due to the consumption of oxygen and whatnot, due to the ongoing biomass. And again, just to speak to this point here, and just a little more caveat. When I say we are solving the Navier-Stokes equations, when I say we're solving the species transport equations, we're not. Nobody is solving these equations. If we were solving these equations, we'd have Nobel Prizes. We'd have Fields medals. All of us in this space are approximating solutions to these equations. And the means by which we approximate solutions to Navier-Stokes is using the Boltzmann transport equation, which works very well on GPUs. That's why we did that. In fact, backstory here, like M-Star was founded right when the K40 came out. We were like, oh, crud, this changes things. And we had all this software. I was working at a big lab at the time with all these tools, and none of them exploited this hardware. And we're like, gee whiz, like this hardware changes everything. And if all these companies are slow moving, we're just going to do it ourselves, which is why M-Star came into being. We're like, we saw these GPUs. We're like, we're going on them. I digress. The system we're looking at today is we're going to look at an XCR 2000. Okay. This is just a GE Healthcare writing. This was later sold off to Cytiva, which is great. We're looking at this production scale reactor. This operates at a few different volumes. Typically, the reported literature is 400, 1200, 2000 liters. You can do higher turndown. We publish a lot on the system in terms of free surface transport, KLA, cell growth. We publish a lot about this system. What's great about this particular system is it's pretty well characterized. Like in this report, they go through and this is cool. They give you a nice description of mixing time as a function of impeller speed and fill level. They give you KLA measurements. They give you heating and cool rates and power inputs and whatnot, and which you can convert into a power number. And so there's a very nice set of data we can use to compare against. And the key point is this, is there should be one model that can appropriately capture all these physics across the range of operating conditions correctly with no reparameterization. And where this really starts to flex is down here in the KLA. If you can have one KLA model, one bubble transport model that captures this range, this order of magnitude variation in KLA, then you know you're doing something right. That's foundationally modeling those physics at the level of the individual transport carriers. Very compelling. Let's get into it, build this model, start comparing the predictions to exactly what's coming out of the experimental report. For many of those who know, or those who know, here's M-Star. Let's build this model. So I need to bring in this geometry to begin. Now I'm going to go ahead and create this from CAD, okay? Actually, I have CAD, I'm going to load it in from my CAD. So I'm going to import this existing file. Let me go to my desktop here, where I was working on this guy earlier. I've got this CAD. So someone gave me like a step file of the impeller and a step file of the vessel. I'm just saying those things exist. I could make it in M-Star if I needed to, but I'm going to do the old CAD import technique here. So first things first, I'm going to load in this tank, this kind of step file tank. At the end of the day, this is an unremarkable geometry. It's just the vessel, as it were. But here I've got my XDR 2000 tank. I can make this M-Star. We've done this before. Here I'm just saying the CAD exists. Maybe my friend in the engineering department made it for me. I see a sparge plate down there. This is also the mag drive where the impeller is going to go. So here's my good old static body. I've got my green bounding box defining the extent of my simulation domain. I can make this smaller if I want to, if I'm going to do a single phase simulation, only have a partial fill vessel. Or I can actually do like a free surface simulation and specify a fill volume or fluid height, as it were, as I'm getting ready to run this guy. So I've got like 1 meter fluid level there. Alternatively, I could specify a fluid volume and have the code just fill it with the appropriate fluid at runtime. Either way, I've got some fluid in there, some simulation domain. Not much is going to happen yet because I have no impeller. Let's go ahead and add the impeller. Just go to create. I'm done adding static bodies. I could add more if I wanted to. I could add more geometry, spargers or T-spargers or probes coming down, but I'll skip that for the time being. Let's go ahead and create our moving body. So we can add as many as you want, of course. I'm just going to add this impeller, which I conveniently made previously. So here's my impeller. It's this 4-bladed pitch blade impeller type thing. This is characteristic of the XR 2000s. Just for those who might be aware, the smaller scale vessels use 3-bladed impellers. So just be aware that the 2000 uses a 4. Conveniently, this pops into the right spot. I can move it around after the fact if I need to. One important point when building these models is to define an appropriate axis of rotation. The code doesn't know how this thing should spin when you load it in. And so foundationally, it's like, well, I'm going to put my axis here. So if I ran this model, the code would think this impeller was orbiting about that red axis there. That's not right. This thing isn't sweeping the bottom of the vessel. I need to tell this code where this axis should exist. So I'll go onto this moving body, define the axis, and I can choose really any surface or edge on this guy and just have the axis mount to that point there. That's our axis. That's where we want our axis of rotation to be. And this particular configuration, I'm at 60 RPM. Maybe I'll bump that up to like 115. And I've got some sort of, this is going to be an up, this right now is actually down pumping because I can see my angle is, my axis is in this direction. So my blade is going to be pointing in the clockwise direction when I look down. Maybe I'll make that negative because oftentimes we look at up pumping configurations with this system. Okay, let's go ahead and just start running this guy to see what we get. I've got my impeller here with my set impeller speed. I've got some sort of fluid level here. Let's go ahead and say this is water-like. I've got a density of 1,000, a kilogram of a viscosity of 10 to the minus 6. I'll use LES versus ILES or DNS. I'll go ahead and model this as Newtonian fluid, and I'll give myself a decent resolution. I'll go up to like 180 or so. We'll talk about this point later, but this informs the smallest eddies I can resolve inside my system. Said again, when I run this guy, I'll hit go here and we'll start cranking the data. When I run this guy, I'm going to be able to see the time evolution of the velocity field around the simulation, okay? And as I look at the time evolution of this velocity field, I'll see structures, I'll see eddies, as it were. Let me go to post and visualize this. The resolution informs how many of what fraction of that inertia spectrum I'm resolving explicitly. Now, I generally can't, at these Reynolds numbers, do a simulation with a resolution that is equal to the Kamal-Grove length scale. That would imply I'm seeing everything. And I've talked about this in previous seminars. Instead, I'm going to be doing LES simulation where I'm resolving past the Taylor scale, but not all the way to the Kamal-Grove. But if I look at this guy here, let's just take a look here and see what we got coming out of this thing. I can begin to see this impeller starting to spin and the fluid starting to inject. I'm kind of watching this guy process as it's coming. I'll go ahead and change this color scale a bit. I'm kind of watching the impeller start to move and agitate this fluid under the action of its spinning motion. So I've got my free surface. This is not doing much yet. I know this free surface isn't going to jiggle around much at this impeller speed and the fill volume. So I'm prepared to handle a vortex, and I'll kind of sneak peek here. Under some cases, I may get a small vortex. This is a previous case I ran to kind of have a one coming out of the oven. But foundationally, I will not get lots of vortex in this system because I have a pretty tiny impeller. And so foundation, I don't have enough kinetic energy to really disperse this guy. But just to foreshadow here, here's where we're going, guys. This is going to be the actual operating condition that we'll get it momentarily, where we've got, gas bubbles, mass transfer, dissolved oxygen, et cetera. We'll speak to that later. But baby steps first. So here I am watching this impeller start to spin. Here is the lattice that was formed by this guy, and I'm kind of interrogating this data as it comes out of the code in real time. So if I look at this here, I can see, for example, the actual like lattice that's being defined by this particular system. That's the lattice that I'm using to solve my Navier-Stokes equations. And this particular Eulerian mesh that I'm using to describe the impeller can be described as something like that. So that's what is actually moving through the system. I'm using in this particular model an immersed boundary method, which means this impeller is passing through, using the immersed boundary method, the Eulerian mesh that represents the fluid. So off we go, and I keep hitting this reload because I'm pulling this data in as it's coming off my GPU, right? Like I'm solving this in real time. And so I'm pulling this data in and interrogating the new data as it comes off. Okay, so that's kind of a quick snapshot of what this is going to look like, how fluid be agitated, what I'm thinking about while building this model. Let's go and start adding some more interesting physics. Let's begin adding, for example, something like some strain and EDR. I want to look at EDR and shear stress. Maybe those things interest me. And also just for those keeping score at home, like this is fully three-dimensional. Like I have some output planes here, and those output planes exist because the code graciously gave me a few to start. It gave me a few output planes here where I'm visualizing data. I can add output planes, or I can just go ahead and look at the full 3D data, like it's here. Like if I snap forward to the full 3D data, here is the system after 7 seconds of agitation, which corresponds to, I don't know, maybe 20 or so impeller turns. Maybe not that many. I can't do it in my head. But here we are kind of watching the full three-dimensional flow field evolve throughout the system. Okay, so that's kind of the first shot across the bow in terms of building this model and understanding what I'm thinking about in terms of resolution, how that's informing my resolution, and let's kind of carry on with that thought. You'll notice here that I use the default time step, and for those who know M-Star, understand what this means in terms of Courant number. The discerning M-Star user might have said, well, John, your LB density is good, not great. Yeah, I've got about a 5% variation. This is because M-Star is explicit, and so it's by necessity quasi-compressible. If I drop my time step a bit, I could get rid of that compressibility. If I drop this time step by maybe 20%, that'll snap down to just a few percent, which would be fine. Okay, I'm also forecasting that I don't need all of this free surface dynamic, and there's an expense here. In fact, if I look at the timing here, look at like where I'm spending my time in this code. So I'm running pretty well, but if I look at how I'm spending time, I'm doing 38% of my time doing Navier-Stokes. I'm doing 30% of my time doing that BOF free surface. That's a lot of tax for a pretty underwhelming physics. Like it's just wiggling around, and maybe at best I get a little vortex. I'm looking at this thing and thinking, gee whiz, I can make this code run like 30% faster if I just turned off that free surface. It's not, and quite frankly, I think it's worth it because it's not a sloshing system. There's not a big vortex. I might get a little dimple here, but for example, and this is kind of forecasting what we're going to see as we go through this. And then here is the full system, and I meant it when I said like we're modeling everything. Like we're modeling all 5 million bubbles breaking them and coalescing. We're modeling mass transfer from every bubble to every voxel and distribution of mass with the system. We're not doing any tricks here. We're going all for the physics because the GPUs allow us to do so. Either way, back to this point here. If I don't need that BOF, I'm going to turn it off. And this is again more in the spirit of best practices. Like M-Star data comes out like that. So you can see right away like what the model's giving you, what you're getting from it, and what physics you may be able to walk back on. Yeah, I'm getting a little bit of wobbles here in the free surface. There's a little bit of like, okay, well, if I go here and I can see a little bit of something there, I'm a little bit of motion, but gee whiz, guys, it's not worth 30% of my runtime. And so I can't turn off the fluid solver. I need that. VOF, that's gone in my next run. Immersed boundary, I need that. Down here, boundary conditions, I need that. Communication at 4%, need communication. Surface statistics, so a few percent. So at the end of the day, like looking at this guy, yeah, this VOF, there's not going to be a lot of motion there. It's taking time. It's gone. So I'm going to go back to this guy and change this just to a single phase simulation. And I'll just drop this fluid height back down to where my fluid volume should be. Let me reset this point here. So if I go ahead and run this guy and look at this, so I was previously running at about 650 million lattice updates per second. Okay. And this would have taken me, it'd take me about another 20 minutes to simulate the remaining 45 seconds of my process. I'm not doing that all right now. I'm going to stop this as it's moving on. But you see, as I walk back in that BOF, this is going to run much faster. Okay, let's go ahead now and start embellishing this to start doing some blend time. Let's begin to compare to some of this measured data available here inside this GE report. For example, they gave us mixing time. Let's run it. Okay, so let's go ahead and do this by adding some glucose. They did acid, I'll add glucose. They're all dismissible fluids. It doesn't really matter. Let me go ahead and add a scalar field here. Now, a scalar in M-Star is a three-dimensional field with a value defined at every lattice point. The scalar evolves, as discussed earlier, via advection diffusion and the conservation of mass. So let me add some bolus here. I'll put in some cylinder of glucose, up near the top of the vessel. Let me go ahead and move this injection site up here and watch this guy starts to spin, okay? And I'll just rename this guy glucose. It doesn't matter what it is. And I'll go ahead and add it to the cylinder here. I'll go ahead and say there's nothing in the background. We'll use base units of volume. We'll do volume fraction representation. And we'll say within this child, at like time zero, we'll just pulse it at time zero. At the time we turn on the impeller, we'll add this bolus of glucose. And let's watch it blend. I can update it less frequently just to help with efficiency. And again, that's something we can speak to later. I'll use the super reflux limiter to help control numerical diffusion, and we'll compare the blend time here to what we're measuring experimentally. Now, I can add probes to kind of see where this glucose concentration is evolving through the system, and this is great. I'll use these probes. Maybe I'll put a probe, I'll put the probe over here, which is where a probe typically is next to XDR. But I'll go ahead and plop that guy there. But in addition to this, the code will organically naturally tell me what it thinks the distribution of this glucose is across the vessel and how it's converging towards a fully homogenized state. So let's watch this guy here. And again, I'll go ahead and with the same impeller speed, and I'll go ahead and run this guy. But now I do not have a free surface because, as I saw from previous runs, I'm not going to need it. It's not vortex. It's not sloshing. I could have anticipated that initially, but in this case, I just wanted to show kind of the speed that comes with it. Okay, so here I'm running faster, a little bit faster, but I did add more physics. Like I added this now scalar field and swapped it with the BOF. But foundation, the important point is this, is like adding this additional physics didn't poison the well. In fact, it had minimal bearing at all. If I go back to post here and watch this guy start to go now, watch this guy start to spin. So I'm running on two monitors, and so when I open M-Star post, it doesn't know where to put it. So it just kind of puts it up across both. I'll do my best to kind of keep it just on the one monitor here. That should be casting. All right, come on, buddy. Let's see if you take. Okay, so here we are, kind of same story as before. But if I look at back to timing, I look at this guy. Now I'm spending 55% of my time doing Navier-Stokes, which is great. I've kind of swapped out VOF for scalar field, but it's only taking 50%. So again, there's an important takeaway point here, is putting on the scalar field and modeling species transport and whatnot, and modeling the addition of this kind of other species that's going to react. That doesn't poison the well. In fact, we're solving the transient Navier-Stokes equations in tandem with these transient advection diffusion equations to predict how species is evolving throughout the system. So if I go to my X-plane here, I can see, if I go to my glucose concentration, like it's there, it's just barely starting to get pulled down. If I kind of watch this guy, there's my bolus. Remember, it added at time zero before the fluid was even agitated at the top of the vessel. Now it's starting to get drawn in, as it were. But foundationally, I'm solving these all in tandem. This means we can do things like coupled viscosity relationships. We can have the viscosity changing in time as the concentration changes, and we get that for free, right? We get that for free because there's so little expense associated with this, or there's no additional expense associated with calculating that viscosity because I already have the concentration. So again, kind of monitoring performance here. This looks good. This looks good. Now, I mentioned that the code is automatically going to be telling us what it thinks this glucose is doing. So I can see here that, well, there was my addition. It went from something to something. Well, there was my addition at time zero. So I've got this kind of constant concentration, which isn't changing in time. That makes sense. It's a closed system. Here I can see the RSD. Now, the RSD isn't doing much, but it's going down, which makes sense because this guy is beginning to homogenize, okay? Let me go to the 3D volume here because it's usually a better way to look at kind of bolus additions being homogenized. But if I look at this guy here, I can see there's my velocity. Let me snap over to my glucose volume fraction. I can see there it is. Here it's starting to kind of go through and start to get drawn down and sucked into that impeller, okay? Okay, let's go ahead and kind of watch this guy go. So watching that guy go, there's my probe. It's not doing anything yet because it hasn't recovered anything yet. But I can see again this glucose started to move on down and get homogenized across the system, which is what happens physically. And again, the important point is, guys, I'm doing this all in real time. Like this isn't a pre-canned solution. I'm pulling this data off the GPU as it's being evaluated by the GPU and visualizing it now. So let's look at some other things as well. I've got this moving body in here. Let's just take a look at it and see where it's converging. It's settling down to a power number of about 1. That makes total sense to this topology and position, and it's aligned with what was measured in the report as well. I can see things like my power numbers, and this is a power. This is a very compelling piece of data, and I'll explain why now. So I'm calculating inside this code the energy dissipation rate. Like I'm calculating like what the EDR is at each individual cell, as well as the resolved shear stress at each individual voxel. I should say not cell, but voxel. This informs cell dynamics, of course. This is a really cool point. Okay. So right here, this black line, this is the total power going into the system via the impeller. Okay. This is just torque times angular velocity. This value is what gives us the power number here, which you can validate experimentally. This red line is completely independent. This red line is the volume integral of all of this energy dissipation rate. Okay, so we're going across this entire domain and calculating the local energy dissipation rate, and we're just integrating that over all cells. Okay, that's what's going on here. Let me try to tailor this because the EDR is rocking around the impeller and it gets lower in the far field. We're then adding up the EDR everywhere. And as expected and demanded by the first law, these guys converge. We are not making them converge. We are not telling, oh, hey, EDR, this is the impeller power number, you better match. The code is satisfying the first law in that energy coming in is balanced with energy being dissipated across the fluid. And wouldn't you know, at early times, power in exceeds power out. And that makes sense because wouldn't you know that early times, the fluid is still accelerating, the kinetic energy is accumulating. And so foundation, this is a critical point. Like if you're going to claim to be getting strain right, because strain, EDR comes from strain. Strain is EDR, or EDR is the double dot product of strain and tensor. But like this is an important point. If you're claiming you're getting strain right, and you can't show me you're satisfying the second law, I'm sorry, the first law, you need to pick up your ball and go home. I know that sounds like that's like playground talk. Maybe I'm being too aggressive, but like this is an important point. Like if you can't show that your EDR, your energy is balanced, how can you claim that your strains are valid? I know I'm talking so aggressively about strain. I don't know why. I need to chill out. But it's like this is an important point. If you're not conserving energy and you can't confirm that your local EDR is valid, how can you hang a KL calculation of that? How can you hang a dissolution? How can you hang shear? How can you hang anything on it if you can't show that you're getting energy dissipation right across the vessel? Here we can, and it's pretty cool. We'll see that get nailed. Like I said, that's like class 1 validation. Power numbers got to match. First law's got to work. And if those aren't working, I don't know how you're going to build a more sophisticated model off that. Okay, because EDR goes into everything in bioprocessing. KLA, dissolution, cell damage, strain, etc. Okay, I digress. Let's go ahead and look at the scatter field as well. As I mentioned, the scatter field is blending, is pushing around. Let me split this guy. The total amount is the same because it's a closed system, but I can see the RSC is getting down. I'm still not very well homogenized. Let's go ahead and look at this guy. I'll change this into a log scale. I'm still, my RSC is like 50%. That's so bad. Let's go and look at this. That's not homogenized. It's nowhere near homogenized. And even the RSC is like below like 5%, 2% to be 95 and 98% homogenized. Let's go over to this guy here and look at this glucose volume fraction. Now I can see this guy's starting to blend. I can start to see glucose going around. Now the probe's going to have something to say, right? If I go to my probe here, let's go ahead and so the probe was just hanging out. Then suddenly, like it gets a signal, like the velocity arrives to the probe. Suddenly it gets a strain. Suddenly it gets a position. Well, the position's always been there. And suddenly it gets some glucose. And like it's kind of evolving here as it kind of sees these spikes. And this is exactly what you see inside the lab, okay? You put probes in different spots. They have overshoots as they're overrepresented by the scatter field. Those are the undershoots. And eventually, as this thing homogenizes, it's going to converge towards the actual equilibrium value. In fact, we know that it must converge to the mean value of 0.0009. This must converge to 0.0 in time. This will snap to that mean value because the probe will be sampling the well-dispersed fluid. You can see we overshot, undershot as we oscillate towards that steady state value. And wouldn't you know, it's the same stuff they show inside the report. So as I'm watching this guy blend, I can see here that I've been spinning now for about 24 seconds. I'm not quite homogenized. And to be sure, this tank started cold. Okay, I started from rest and just sort of agitated it. But I can see here that's probably going to take me like, and now I'm starting to do some meaningful blending. I'll probably get there around like 35 seconds, which means if this fluid were, if the system were already agitated to begin, it'd probably be like a 25%. And I could do that, of course. I could put the bolus in after the fluid is agitated. I could just delay the start time. I could go over to this guy and just say, well, add the glucose at, 10 seconds or whatnot. But at the end of the day, I'm getting like a 20, 30 second blend time. Like, does that make sense? Is it reasonable? Yeah, it's reasonable. We're operating on 50 RPM, right at about 1,200 liters. We're right at about 30 seconds, okay? And again, the neat thing, guys, give me any fill volume. Give me any operating speed, and we'll nail these guys. We'll nail them. Because quite frankly, we're not reparameterizing the model. We're capturing the transient physics. We're doing it at time. And it allows us to, again, build one model that handles every operating condition, at least within this case. So again, we'll let this come to fruition and let it blend. It's almost done. I'll stop here soon because once you get to 90%, it gets hard to see. Like there's still differences, but they get a little trickier to see. Let me change the color scale here so I can kind of anticipate them some. They're there-ish, but like it's hard to see at 90% homogenized, but the math can pick it up. You can see a little bit there. Let me go ahead and just kind of tighten this guy down a bit, just if I can do something to kind of make it more interesting for y'all. But it's, yeah, a little bit there. But either way, it's going in. The probe is settling in right where it should have gone to per the mean glucose concentration, and our RC is going down as well. We're going to call this one. Okay, now, so it's very easy to do these LES simulations, these glucose mixing simulations. And again, one more point of resolution here is like, oh, is your resolution good enough? Is resolution good enough? What should resolution be in LES simulation? 2 points here. One, our power number is snapped into place. And I know it's going to work because I've written about the slot, both in our documentation and the literature, but you can test that and see the power number no longer converge to the resolution. And also the fact that we're satisfying the second law. I'm sorry, I keep saying the second law. I don't know why. The first law tells us that we're resolving all the way down to the Taylor scale and beyond, such that the LES filter is just mopping up the subgrid stuff as it was designed to do. If your filter is too big in LES simulation, such that your resolution is above the Taylor scale, that's when this starts to break down because you're asking the subgrid filter to mop up eddies with structure, with shape, as it were, some anisotropic eddies. And so as long as you're, and I've spoken about this at length in our previous webinars, you can look at them. When I talked about DNS LES simulation, what it was called DNS CFD on GPUs or whatnot. It was last December, I think. But foundationally, as that filter gets small enough and that resolution gets small enough to be smaller than the Taylor scale, the simulation is going to work great because that point is doing what it was designed to do: mop up rapidly thermalizing eddies as they go down into the Kamal Grub dumpster. So there we go. They're looking good. If we ran this double the resolution, we'd get the same sync results in terms of power number, EDR, etc. A KLA blend time too, because it all hangs on EDR. This guy's ready to blend. He's at like 97%. We're getting about 20, 30 seconds or so, depending on when we started it. That's in line with the measured data. Okay, let's start adding more. Let's make this a multi-phase simulation. I'm going to disable this glucose here because I don't need it anymore. And I'm going to add in some gas bubbles. And I saw a question, Chalakarn, about gas bubbles coming in through microsparge down here. So in this XDR 2000 system, we have 8 microspargers, okay? Now, the bubbles coming out of microsparge are not the size of microsparge. And this can be a discussion after the fact. There's actually some nice literature that explains what the bubble size should be, and we have that baked into the code. But I'll just kind of caveat that point momentarily. A 20 micrometer microsparge does not produce 20 micrometer bubbles, okay? There's published data with cameras down there that show what they come out as, and people develop correlations that speak to that. I'll evoke it and then point in the right direction where to look that up. But I need to tell the code to start adding bubbles to those points there. I'm going to do this by adding a bubble zone, okay? These gas bubbles. And the bubbles need a geometry in which they're going to be added. So same logic applies. I could import the sparge geometry from CAD, or I can just build it right here in M-Star. Now, I got a couple options here. I could do the lazy man sparge, which I'll start with. Then I'll go on to the detailed man sparge. The lazy man sparge looks like this. He kind of squints at it and says, you know what? I know I've got 8 microspargers, but quite frankly, they're kind of small and close. I'm just going to go ahead and use like a torus and just say, you know what? I'm going to go ahead and say that inside this torus, let me go ahead and move this guy. I'll right size him so he's kind of right sized at least. I'll be able to move this guy over here, and I might kind of bring him up here and be like, okay, let me rotate this guy. Like, this is the lazy man sparge, where it's like, you know what? I got bubbles coming in somewhere down below the impeller. It's good enough. I'm just gonna have them go in there, and I'm gonna start with lazy man's, then I'll do sophisticated man sparge. But to be sure, it's probably not a bad approximation. Like, it's not as good as the micro sparge, but foundationally, I just say that bubbles are coming in everywhere along the surface. If I wanted to be more exact, I can either make that in CAD, or I could do it here. I'll just illustrate this real fast. Like let me just delete that. And let's just go ahead and make the actual sparge. Let me go ahead and put in some little primitive cylinder here. And let me measure some guys here. Like, how big are these guys? Those guys are like, okay, 0.24 centimeters in diameter. So let me make this guy 0.24, and its length isn't super important here. Let me go ahead and kind of do some more measurements here. What do we got? What's the diameter of this guy here? That's like 0.64 is the distance. Okay. So let's just do like, I'm just kind of making this inside M-Star. Let's just do some sort of like duplicate object pattern. Let's do like an arc pattern. Let's do like a, I'll do something like this. I'll give myself, I've got like a 45 degree and I need 8 of them. And this diameter here was like 0.16, if I recall. If I can adjust that for the fact. Okay, good enough. So I'll just kind of add those guys in. And now I'm doing the sophisticated man sparge. And I'll move this guy up. And now I've got like, for those who are really, interested in getting this right, which I'm interested in getting it right too. I've got, again, you can do this in CAD after the fact. I'm just kind of showing how to do it in M-Star now. Let me go and just kind of anchor this guy just right and kind of get him one more time. I'll do 2 more moves and I'll be done. Over. Good enough for me. And again, because I'm on a call, I'm trying to get this done. Good enough. I can move him down. Good enough. I'll just leave him there for the time being. Yeah, I'm sorry. I've got to move one more. I'm not that lazy. Okay, good enough. So now we're going to have spargers coming in. Now, we need to specify the initial bubble size. Okay. Let's go ahead and specify this. So we can do some sort of gas flow rate. Maybe I'll specify like, 4 liters per minute. That's fine. Or maybe that's perfectly fine for the system. I can use what they did in the GE Accelerex engineering note. For initial bubble size, I'll have it come in at time 0. I can specify size distributions, or I can use the calculator. And there are good correlations for predicting what the size of the bubbles will be through various structures. Okay, like if I have a porous disparger and I know certain properties of it, I can then understand and predict what the size should be. I'm just going to put in a value here of like 3 millimeters just to get started. But I saw the question, Jenna Card, and to be sure this question is addressed in our documentation, I'm not going to go through it at length right now. But yes, there are correlations that allow us to predict what the bubble size should be, and you can evoke those. In fact, the right spot of docs would be here. And docs is your friend, remember. Docs is your friend. If I go here to create, let me go to particles, let me go to my bubbles, just to kind of put see if I can find the initial diameter. We've got kind of a discussion of the calculator and the size distribution and where these things come from, and experimental study of bubble metals, porous spargers. So this is all discussed here. But to be sure, I'll just put in like 3 millimeters to start. Okay, let's go ahead and run this guy. I'm going to turn on breakup and coalescence using the built-in models. Just kind of watch this guy go. And let's watch this guy start to spin. I'll have this breakup and coalescence start at time 0, just so we're getting the whole size distribution. Okay, just for those who are still wondering, here we have our mixing. It's starting to settle in. It's getting homogenized. We're at like 99.7% homogenized. This guy's wasted. Okay. Let's now run this simulation with the gas bubbles and the sparge flow. I'll give myself more gas, give us some more things to look at. I'll turn the simulation to at once, of course. I can run as many as my GPU memory can host. But I'm going to go ahead and just kind of keep this guy kind of get us through this presentation. Okay, off it goes. So now we have gas bubbles being sparged into the system. We're explicitly tracking all of them. They're coming into the sparge. I took a little haircut. My speed has gone down a bit because I'm doing now extra math. I'm tracking now almost 10,000, soon to be 100,000, soon to be maybe a few million bubbles, which is fine. But there's a little bit of haircut there. But foundation, it's not a showstopper. Like, to be able to visualize and study and characterize these multi-phase systems, like, it's still running in minutes. Right? It's not like, oh my gosh, I can't do that. This is going to shut down our presentation today. It's happening now. It's a few percent swing this way or that way. Sorry again with my monitor. But either way, there are the bubbles coming up, beginning to move through the system under the action of the agitator. Let me turn off these fluid sizes because they're not terribly interesting to me. And I'll go ahead and render these by size. Let's go ahead and look at these in their true form. So I've got tiny bubbles coming out of the sparge. I can see them coming out there. I gave them 3 millimeters Totocron, but they undergo breakable coalescence events, of course. And I can see some bigger bubbles starting to rise. I'll pull in my newest data. And I can see here I'm starting to get, again, this impeller spinning, the bubbles rising. We can see things like a size distribution, as it were. If I go to a histogram and do some sort of, diameter, I'll give myself maybe 50 bins here, and I'll normalize so it's not jumping around. I can see my size distribution. Look, there's a lot of breakup going on because I brought them in at 3 millimeters, but the impeller is breaking them up, obviously, and causing the distribution to be clearly non-uniform. Just to illustrate what I'm showing here, this left axis is like fraction. That's the fraction of the bubbles with a given diameter. And that diameter is measured in meters. So here I'm kind of watching my histogram kind of evolve and snap into place. Now there is coalescence going on, so I get some big bubbles up here. But foundationally, I'm just kind of watching this guy spin and converge towards its steady state. Let's look at the bubble count here and see how we're doing. My bubble count is still rising. I'm not yet at steady state, right? My bubble sizes, my mean sizes are changing. My injection rate is not equal to my removal rate at the free surface. And so I know that I'm not at steady state. As a consequence, the bubble count is increasing. I'm coming up here on 1 million bubbles, but no sweat. GPU has no problem with that. If I look at timing, there will be a haircut here. If I go to my timing, it's taking time as I get to 1 million bubbles on one. I'm running this on a laptop GPU, as it were. But the important point is this, is I can comfortably model millions, tens of millions on a desktop GPU of these bubbles explicitly. And because I can model these bubbles at the level of the transport carrier, that bubble model doesn't change, whether I'm in 1 liter or 2,000 liters, which is pretty compelling. So this guy is not yet at steady state. He's still churning around, but I can see the bubbles beginning to flow and move throughout this system, okay? The size distribution is pretty well set. At this point, we're just kind of getting more and more bubbles trapped and dispersed throughout the system, okay? And these are right size. I'm rendering them by their true size, as it were, in this visual representation, as described by this histogram here. So this is taking some time to cook. This take a little time to cook. In fact, if I just kind of peek ahead to the case I ran previously, just to kind of get ahead for today, I can see here that if I go to my bubbles, it takes about, 90 seconds, maybe 2 minutes for the bubble size to become the bubble count to become fully satisfied. And in fact, I ran one longer than that. Let's go over here if I can get it to my bubbles. Like this guy snapped into place. Let's see what we got here. Sorry, just take a second here to load up. Yeah, it took about 2 minutes or so for the bubble size to really snap into place, which isn't unsurprising. It takes time for a cubic meter of fluid to be agitated for the bubble size to all converge, the size rate to snap into place, and in fact, the addition rate to match the exit rate, which is indicative of a steady state simulation, at least for the bubble field. But as I'm looking at the sizes converging, I'm looking at the count converging, and the entrance and exit rate converging. And once those all settle, I know my KLA will be constant. Okay. So this guy is not going to get there in the course of our discussion now, but you understand how these gears are turning. Now, I can do more than just watch bubbles go. I can actually couple those bubbles and watch how they transfer mass and oxygen to the surrounding aqueous phase. Let's go ahead and do this. Let's go ahead and create a scatter field. A scatter field is not glucose this time. Instead, I'm going to define it as DO2. And I'll say there's no DO2 to begin. Somehow this is just totally stripped of oxygen. And I'll go ahead and couple these gas bubbles to the DO2. We talk about this at length in our papers. We talk about this at length in the documentation. If you have questions about this, call. but I'll just evoke the automatic criteria here, where I will say, I'm going to model interfacial mass transfer. I'm going to calculate KL on a bubble by bubble basis. I am going to do scalar coupling. I will track DO2. I will say that these are, say, air bubbles coming in, 21% oxygen, with a given molar volume and a given solubility. That informs what sort of mass flux we'll see. KL is the convective mass transfer. This describes the transfer rate as a function of the concentration difference and the convective mass transfer coefficient KL. This is all calculated on a bubble by bubble basis. So when I go and run this, let me stop this good one here. I now have oxygen coming in through the bubbles. We could have any number of gases in these bubbles, transferring to the aqueous phase or not. But in this case, air coming in with oxygen in it, oxygen moving from the air to the surrounding aqueous phase, that oxygen being mixed in the aqueous phase, the bubble mixed as well and moved as well, the bubble eventually broaching the surface. And because of that action, I'll have oxygen accumulation throughout this vessel until it achieves some saturation limit. Let's watch it. And I can use this to predict dead zones, oxygen dearths, as it were. And I'll show that momentarily with my previous run simulation. I look at where oxygen's going, where oxygen isn't going, where bubbles are going, where they're not going, and how, here's an important point, my bubble composition is changing. This is a very important point, is that as air bubbles give up oxygen, they bring less to the party. And as a consequence, in a very tall vessel, very large vessel with very large resonance times, your bubbles begin to become less effective. We can capture that. We can capture the stripping effect as it works. Should they be stripping CO2? I didn't include that right now, but you can see the natural induction into modeling these physics. And again, I know I just clicked the button, automatic. We've published dozen papers on this in the last few years with many of you in this audience validating this and showing you how these models work and, more importantly, why they work. So let's go to this guy and watch now. And instead of visualizing velocity or scalar fields at this point, I'm going to go ahead and look at my DO, because I've got DO coming into the system via the bubbles. So we're going to snap over to this 3D volume here and look at this guy. So there's velocity hanging out doing its thing. There are my bubbles. I'm going to turn the bubbles off temporarily and go to my volume and look at like my DO concentration. And look, I can like see DO like in the aqueous phase now. How did it get there? The bubbles. If I look at the bubbles, I can see, let me colorize them by their DO concentration. I can see that they're actually losing a little bit of oxygen, which is not surprising. They're coming in very oxygen rich, but the longer they stay, like they lose oxygen and they stop participating, as it were. This is real. This is what happens in a bioreactor. And it's physics that are very easy to capture and incorporate inside a model like this. I can see there's some bubbles here that, yeah, essentially have lost almost a third of their oxygen, as it were. But here I see, for example, if I go ahead and jump over to this, let me see what time I'm at. I'm coming up on 3 seconds here. My volume, I can see oxygen kind of moving through the system, kind of following the bubbles, as it were, because the bubbles are what's causing the oxygen to go exist in the aqueous phase. It's kind of neat to see that oxygen plume following the bubbles as they emerge throughout the vessel and watch this guy buzz. Okay, this will eventually converge towards a saturated state, right? Eventually, the bubbles keep pushing oxygen in until the oxygen concentration in the dissolved gas matches the saturation limit and there's no more oxygen transfer. So if I look at this here now, I can look at my scalar DO. Right now, my concentration is going up, but it's got a long way to go. But this is my DO concentration. And if I look at my transfer rate, I can see that, you know, I'm getting more and more and more oxygen. The moles per second is going up because, quite frankly, KLA is still converging and bubbles are still increasing in the vessel. So the transfer rate's going up. Eventually, it'll reach some sort of quasi-steady state. And eventually, it'll go down to zero. And it'll go down to zero as this oxygen concentration goes up to become saturated, which means there's no longer any mass transfer from the bubbles to the aqueous phase. We're a long ways from that point in this simulation now, but it's cool to watch the oxygen accumulate inside the water as the bubbles move about and participate in very chemical coalescence events. And again, guys, like this is like my 4th simulation. Like that's the point of that kind of paper I was referencing earlier. Like, you know, that like it's absurd what I'm doing live in a webinar on a laptop. Okay, then I'm running these multi-phase oxygen transfer, blending LES simulations with a million bubbles. Like it's bonkers. And it's all thanks to the GPU. And if a code can't do that on a GPU, that code isn't designed for GPUs, tell you that much. But again, when you have a good code that's born and bred to run on GPUs, this becomes your playground. Okay, and it totally changes how you simulate, as opposed to like this kind of like going to simulation white knuckled and hoping it runs after a week. It's like when you're iterating like this and dynamically building, getting feedback and seeing and changing, it changes how you simulate flat out. Now, there's one more bit of physics I want to add that I'm going to have to pull out of my Easy Bake Oven, but I'll illustrate how I'm adding it here. So if I go to my model, let me go ahead and go back over this guy here. I can also add biomass. Like I can add, and I'll model that via an ongoing chemical reaction. So I'll add a fluid reaction here, and I'll call this guy like a biomass. And I'm just going to say that the effect of the biomass is just like consume oxygen. Like I'll call this OUR, and this maybe it's like 0.5 e to my 7, or maybe it's 6. Like these are measured values. This is moles per liter per second, of course. And so I'll say my rate OUR is equal to, minus this. So this is the rate at which I'm gobbling oxygen up inside my system. So just as every single bubble individually is contributing to oxygen transfer on a bubble by bubble basis, every single voxel individually can contribute to oxygen consumption. So I can now model how I'm seeing spatial variations in DO as oxygen bubbles are putting it in there and the biomass is gobbling it up. I'm not going to have time to run this right now, but I've got it out of my Easy Bake Oven. Here was me running. I ran this. I started this just earlier. So I got about maybe 200 seconds or so of simulation time. And I can see, for example, they're all my bubbles. Let me turn those off because I've got a fair number of them. And I've jumped onto a desktop. This is not a big desktop. It's a Titan RTX from like 7 years ago. It's a very modest computer. But like in this guy here, balance looks good. Let's go over to my bubbles here. I've got about 22 million bubbles. It's beefy. If I go to my KLA, let's see what KLA I'm getting here. Let's take a look at my KLA down here. I'm getting a KLA of about 0.0032. That checks out. If I go back to this measured data here, I'd be expecting something around 10, which is about 0.003. So yeah, KLA is checking out against measured data, and I could survey that whole landscape. We do all the time. But foundationally, but here's the thing. I now have, for this DO, this oxygen transfer from the bubbles, as well as ongoing consumption. And right now, I'm pouring more oxygen in than I'm consuming. As a consequence, my mean oxygen is going up. As this mean oxygen concentration goes up, my OTR rate goes down. There's less of a driving potential. And this will go down until the transfer rate balances the consumption rate, and the concentration that achieves that flatlines. As the code will get that. It'll get it. And as I go over to this guy here, let me turn the bubbles off. And in that process, I can see, for example, here is my DO concentration. I can see I've got like high concentrations there and a region 30% lower up here that's just standing inside the vessel as I compete between transfer and consumption. And even when I get to a bounce here, even as these guys bounce, once DL converges, this gradient will persist. But look at what I can see here. I can model this like multi-phase gas cell system. I put the free surface on here with this ongoing reaction to see where the oxygen isn't. And like, that's how you build a bioreactor model. I can see that I'm satisfying the first law in terms of mass conservation with species. I can see that I'm satisfying the first law with energy. I can see that power numbers checking out. It's pretty cool. I can see that my KLA is checking out. It's pretty cool to build these guys. We're running low on time, so I want to get to questions. But guys, like this is the point. And this is what I think are the best practices, as we can build these mechanistically sound, mechanistically described, and carrier level models. We scale incredibly quickly with both runtime and complexity. And if we can interrogate not just ancillary questions like, oh, what's the blend time? What's the KLA? The KLA isn't the point. The oxygen is the point. And rather than just answering the ancillary question, we can just look at it and figure out what's going on inside the vessel and how we can improve that process. Okay, I want to leave a couple minutes for questions. Thank you so much, Amber. I'll bounce back to you to kind of parse through these as needed. But yeah, that's as much as I wanted to show just for now. And I want to leave just at least 2 minutes for questions.
Great, thanks. I think you probably have addressed the first question, and then the second one I think may have been answered by a paper that Eric mentioned. So if that is not an adequate response, please reach out to us and we'll get back. So we'll get back to you. So let's go on to the third question. This session is very intriguing, John. I am modeling a case with combo bottom impellers and a bioreactor. Well, we add 2 impellers as a moving body. Is it possible to try running them at different positions to each other, or will they be always at a particular selected point of coordinates?
You can do whatever you want to do. And so just to kind of, there's 2 ways to get at that. One way is to do a parameter sweep where I can, actually have the simulation march through a series of serial simulations or run them in parallel and edit kind of where a system might be. So maybe I'll go to this guy and change the mount point, as it were, the motion axis, or any of these parameters associated with this guy. And then I can run a series of simulations. Alternatively, if you want to, you can actually have the impeller move throughout the simulation. Like maybe it's one simulation and it's at the bottom, and then at T1 seconds or T10 seconds, it moves up while continuing to spin and is at the new location. So yes, and Brownie, that might be a sidebar conversation, but yes, either as a parameter sweep or within the context of the model, you can have that impeller position moving in time. Absolutely.
Okay, one more question. Can M-Star capture the slurry flow through microchannel 100 micron to 500 micron? What lattice resolution will be needed to model such flow through a small gap?
Yeah, so foundationally, your resolution is informed by your characteristic system size. If you're looking at, and we can do capillary flows and, we can do capillary rise, that's on the code. That's not relevant to this discussion here, but certainly, yes. You'd want your resolution to be at least a few dozen across that capillary gap in order to get the contact angle modeled correctly, as well as any velocity field should you need it. But microfluidics, as it were one of the first applications of LBM, like flow through porous media. So yes, low Reynolds number creeping flows, contact angle driven flows, microchannel flows, that is bread and butter M-Star.
That's great. I think we're at time here, and that covers all the questions.
Thank you, guys. Thanks for your great questions and attention today. I appreciate your time as always.